Hello, my name is Wayne Strasser from the Fluid Group at Liberty, and thank you for your interest in our effort to validate a VOF-to-DPM methodology using a flow blurring atomizer. I'm especially grateful to my colleague, Dr. Zhang from Baylor, who collected the experimental data for this work. For the viewer that may not be intimately familiar with atomization, I'll go over a few basics. This is not a new technology. We've been studying this for about 200 years. Very important for many industries: agricultural, fire protection, energy production, chemical and food. And even back less than 100 years ago, we began looking at spray modulation. And I don't cover that information here, but it's an important aspect of atomization where an external forcing function can be used to perhaps modulate the atomization and improve its efficiency. But among all these different processes, there are a few common pathways that the atomization process takes, and they're not always in this order, but we'll address them best we can. But as we begin with a Newtonian liquid with low Reynolds number, the initial perturbations come from the Kelvin-Helmholtz shear instability as the immiscible interface interacts between the two fluids at different velocities, and that excites that interface, and that leads to either concave in, concave out perturbations, and that takes on the form of perforations or tongues depending on which direction they're curved, and that's going to necessarily exacerbate or I guess capitalize on the Rayleigh plateau instabilities, and that's going to produce droplets. They're going to break away, and if conditions are right, we'll have secondary breakup as well. But for a Newtonian liquid with high Reynolds number, the situation might be slightly different, in that the initial perturbations might be augmented by liquid phase turbulence. And all the additional features will take hold after that, but that might be the initial cause. Now, my group is focused on cold non-Newtonian liquid being atomized by a hot transonic gas, and that's interesting because there's this instability cycle in this situation that's self-amplified. And I'll show an example here. I apologize for the delay in the technical glitches on the previous slide, but anyway, this is our first example of what we call wave atomization, wave augmented varicose explosions. And this is an animation of the inside of our atomizer. The flow is generally from left to right. The liquid phase, or the slurry, is entering from the bottom left-hand corner, and we've taken this azimuthal geometry, this circular geometry, and flattened it out or unraveled it into a Cartesian coordinate system for us to examine the inner wave. The backdrop, the back wall in this picture is colored by Mach number from 0 to 0.8, dark being lower and light being higher. But the surface itself is colored by pressure, with light being lower and dark being higher. And you see this regular, repeatable, three-dimensional structure of the wave as it breaks through the atomization region and moves toward the outside of the nozzle, which is about the center, about the middle point of this figure. As we continue looking at our wave example that my group has been focused on, let's look at the left-hand side first. That is a crosscut through the nozzle of contours of Mach number, and you see that the steam, what's coming in from the center of the left picture, is being accelerated as a high blockage ratio wave breaks into that stream, and that acceleration is going to create heat, it's going to create pressure, and the flow is going to accelerate to a transonic condition as the droplets are stripped off those waves. And you look at the outside of that scenario on the right-hand side, where I've got the liquid interface colored by strain rate, where yellow is large and the darker color is low. We see those waves collapse from the inside to the outside, and how that causes these radial bursting events. Now we direct our attention to the topic at hand, which is flow blurring atomization. This is not the internal wave generation system we just described. That was just an example of what my group has spent time focusing on. Here we look at this nozzle design, however, with air on the outside and liquid on the inside of the primary atomization space. In the upper left-hand corner of the picture, in the bottom right-hand corner, you see an example of the gas coming in radially from the outside, entering a vertical liquid stream. All direction primarily is from top to bottom in flow. And by the way, this is a figure out of my colleague, Dr. Zhang's paper. This is not my work. But there are two important diameters here, as shown in the upper right-hand corner of this figure. Is the capillary diameter, which is what the liquid path involves, and then the orifice diameter, which is what occurs after they meet, and then the height h between them. But if flow blurring does occur, and I'll describe the transition here in a minute to some extent, but when flow blurring occurs, you see that the gas penetrates the liquid phase, and in fact, depending on the nozzle orientation and buoyancy, the gas can actually pass upstream of the liquid, and it helps to break the liquid up. It destabilizes it, as you see in the bottom of the figure. You have, depending on the pressure drop across the orifice, you have a sudden expansion of an air bubble or a gas bubble inside the contiguous liquid stream, and that's going to produce rupturing and eventually smaller droplets. So that's the flow blurring scenario. But flow focusing, you could picture the same situation without the central stream being permeated by the gas phase. So the gas expansion, though, is going to lower those turbulence length scales. It's going to induce an effervescence in the nozzle and change the way the system behaves, which is what you want in this case. But it turns out that for a given liquid flow, Q dot, the height and diameter ratio, the DO is in the orifice diameter, those become very important parameters, and they're a function of that transitional height normalized by DO is a function of the other diameter ratio to the 1/4, and that was given in some prior work. I didn't develop this. But alternatively, though, for a given geometric ratio, geometric scenario, you can actually have a minimum liquid flow to create a transition. So if you can imagine, liquid momentum and the gas momentum are always battling for space where the interface is produced, and in the situation where the liquid is ramped up, the gas will have no opportunity to penetrate that high density, highly viscous fluid. So this particular paper in 04 says that this design is an order of magnitude more efficient than other air blast geometries. I would argue that perhaps our WA.V.E atomizer might exceed that, but we've not compared those. Now, to be very specific for our situation, our dimension and flow rates are two diameters are equal at 1.5 millimeters. The height is 3/8 of a millimeter. We're using C3 biofuel and air being fed both at the same rate, 1.7 E - 4 kilograms per second. C3 is a blend. It's nice that it has a high flash point of JP5 for nice handling characteristics, but also a higher C10 number for ignition delay. The gas-liquid momentum ratio is about 670. The Mach number of the feed gas is about 0.23. Depending on what you use as your length scale, the dimensionless numbers will be different. So if we take our length scale to be, our characteristic length scale, and the Weber number to be solder mean diameter, Weber number is about 17, Reynolds number is approximately 300, and on a surge is less than 1.18. And if the dominant frequency is about 1,000 hertz, which is what we expect from some preliminary work, the true hole number is about 1 E - 3. However, if you take the length scale, the characteristic length scale to be the orifice diameter, things change. The Weber number is 440, Reynolds number is 7,500, on a surge number has fallen to 0.036, and true hole number has fallen in order of magnitude. But in general, we can characteristically say that we're at moderate to high Weber numbers, moderate to high Reynolds numbers, and low owner surge numbers and low screw hole numbers. Let me first offer a correction from our previous slide. I would probably say that the Reynolds numbers are moderate, not high Reynolds numbers. So let's look now at a cross-section and some of the views of our mesh and our blocking system to control mesh growth. On the bottom left-hand corner, we have this 90-degree situation where we're taking periodic planes on either side, and we'll discuss that more throughout this document. So we have biofuel down the center, and those different colored regions are for the blocks, again, to control mesh growth. And the typical mesh size we're starting with, we call this the base mesh, is M1, about 1 million cells, all hex, almost all structured, but some unstructured, but all hex nonetheless. And that would be about 4 million for a full 360 azimuth. The outside of the mesh is shown on the right, and then center cuts along those periodic planes is shown in the bottom center, and you see the different flows of the materials. There are about 80 cells across the orifice diameter, resulting in approximately a 20 micron typical mesh length scale MLS. Now, we only really care about the circular region downstream of the orifice of a radius of 1.5 millimeters and a distance, of 5 millimeters to compare with the experiment. So all we really care about is that downstream region, and that allows us to save a little bit of computational time downstream, because of course we could take this to absurd distances and look at secondary atomization and all that, but we're not. As we continue now and think about mesh refinement, we do some mesh sensitivity analyses, and I'm showing three meshes there on the right, and they're overlaid on top of one another so that we can compare them. But for each case, M1 remembers the base case, but to go to M2 and M3, we cut each cell in half in all three dimensions, resulting in a 7-fold increase in mesh count locally there wherever we're refining. So it's a 7-fold increase, making an 8x final number. But so from M1 to M2, we go from about 1 million to 7 million cells because we're not refining the entire model, we're just refining where we care about. And so the mesh length scale across the orifice, or the bulk mesh length scale in the atomization region from the orifice down is about 10 microns. And likewise, we did mesh 2 to mesh 3. Now we have about 53 million hex cells with about 5 micron mesh length scale across the orifice in the downstream region. Now remember, this is all for a 1/4 model, so everything here would be multiplied by 4. So we want to move this to a 360-degree domain. Let us now review our methodology. This is a VOF technique, and this picture belongs to someone else. I didn't do this, but we're using, like I said, VOF, and the point of VOF is to resolve the subgrid scale liquid-gas interface, because CFD typically is only concerned with cell-centered values and an average volume of fractions, say, for a given cell. And those volume fractions for the cells are shown in this picture on the right, and we're sketching the outline of the actual interface in the background, and then the replicated piecewise linear interface construction is shown there in segments. So what the method uses, though, is it looks at the spatial averages and their derivatives and then comes up with an estimate for the position of the interface. And then from that, you get the advection of the phases, because then you know how much of each phase is present on each wall. Now, we do use curvature in VOF, but the curvature is not used to reconstruct the interface because there is no curvature in the interface. But it is used for the pressure balance, the normal Laplace pressure for curved interfaces, so that we can take into account that correctly. Now, the obvious alternative to VOF is DPM, discrete phase modeling. And that uses a Lagrangian approach to use Newton's law of motion to resolve the path of each droplet, whether it be a droplet or a parcel, a group of droplets, however the code phrases it. Looking at the acceleration, local acceleration based on drag, virtual mass buoyancy, again, this is Newton's law of motion, so it's the sum of forces acting on the droplet. And there's a picture in the bottom left-hand corner that's not from me, not from my work, but this shows the tracking of the droplets or particles through a given cell. And this is exactly the opposite of VOF. So VOF assumes there are many cells per droplet because we are resolving the interface explicitly, or implicitly in some cases, but in our case explicitly. However, DPM is the reciprocal of that says there are many droplets per cell. So which one of these wins? Neither. I want both of those. So in Fluent 2022 R1, we have this feature where we can combine VOF to DPM, and the premise is this. Let's resolve the VOF interface wherever there's an interface. But then when curvature or droplet size relative to local cell size becomes insufficient for resolution, we move everything in the cell, its mass and minimum energy, to DPM parcels. And the cell count should be able to be dramatically reduced because in the regions where we would have very, very small droplets, once that's converted to DPM, we don't need to track their interfaces anymore. So here's a picture, an example from Dr. Ling and his group from 2015. Again, I did not do this work. The left-hand side is their DNS simulation. The right-hand side shows what's happening when they're using a VOF to DPM type strategy. They don't call it that exactly, but the concept is consistent, is analogous to this. In the right-hand side, the darker droplets represent those that have been converted from an interfacial reconstruction situation to a parcel or a particle. They call it the point particle model, but either way, you see they're spherical, they're small, and there's a close representation between the right and the left without resolving each droplet explicitly. Before we get into our results, I would like to discuss the effect of azimuthal angle. My past work, atomization related, showed that azimuthal angle was irrelevant beyond 90 degrees. In fact, I used some models with even 11.25 degrees, and everything was still reasonable. The droplet size was, say, 10% different. However, that involved an annular liquid. So the primary source of instability, that interfacial action, was taking place mostly in an annular region outside the central stream. However, in this situation, we've got this undulating liquid stream. This is going to be a major problem using periodic planes, and I'm clarifying or giving the caveat that this is at least an ANSYS. I'm not sure if others have this figured out, but we have some problems. So we're going to begin with some demonstrations of these problems, something for the reader to be careful for. But first, let me talk about where I'm going to be doing some sampling. This is a side view of the nozzle and contours showing that the stream's meeting. And there's no phase differentiation here. This is just time average velocity contours from 0 to 180 meters per second, moving down the nozzle. And superimposed on that are red dotted lines. Those represent the planes I'll be doing crosscuts on to post-process data. X equals 0 starts at the end of the beginning of the orifice there, marked with the green line, and then the spacing of each of the planes is shown on the right, 0.125 millimeters, 0.25, and then there's an error at the bottom that should be 0.5 millimeters for those planes at the bottom. The convective time scale that we're going to be talking about during this presentation is the average length of time it takes for stuff to make its way from X equals 0 to the outlet of our model. So we call that a unit convective time. Now our first demonstration of this. The animations on the right are isosurfaces of liquid, and the one in the center of the slide is a 90-degree model. The next one's 180, and the right side is 360. And anything you see that is not showing as an interfacial reconstructed interface there, or an isosurface, is where material has been converted from VOF to DPM. But you see very different situations moving from left to right. The 180 is reasonably close to the 360, but 360 is unique. The liquid stream is allowed to dance and undulate and provide another instability mechanism as opposed to just Kelvin-Helmholtz to change the paradigm of what the atomization looks like. So this is clearly a situation where 90-degree model is unacceptable, and I would even argue the 180 is as well. Likewise, here we're looking at a plane that is negative 0.125 millimeters up into the nozzle. So in other words, just right up and above the beginning of the orifice marked there in the green arrow. Again, we're looking at animations, and where blue in this situation is the biofuel. From left to right, we have a 90, a 180, and a 360. And I would argue that the 90 and 180 are very similar. We still see a quadrantid type flow, rotation, but no undulation, and the undulation can begin in the 360 model, where we give the freedom, give the stream latitude to dance across various coordinate axes and go into to develop its full instability that it would desire. Continuing on this investigation to the effect of azimuthal angle, let's look a little farther down into the orifice now. We're at 0.5 millimeters, where we have a similar paradigm of 90, 180, and 360 in the bottom. And here we're looking at contours of velocity from 0 to 180 meters a second in the same coloring range we've shown in the past. The 180 is deviating significantly from the 90. You do see additional latitude there, but the 360 again is unique, as we can cross coordinates, cross the axes, and get a much more variable response and more instability developed as the stream takes its shape. Another super important feature for any unsteady situation, whether you're using CFD or an experiment, and I can't stress that enough, this is for CFD or an experiment, you need to allow the model to become quasi-steady state, or the experiment to become quasi-steady state, before you consider it characteristically stationary or statistically stationary, so you can begin collecting data. In this case, I've got an example of air inlet pressure, the transient signal from that versus convective time. And remember, convective time is the unit of time it takes for the material to make its way from the orifice to the outlet of our model. And you see that it takes about 400 convective times before that signal takes on its final form. We see an initial upshot in the beginning, what looks like a quasi-steady solution up until about 200. Then from 200 to 400, we change character again. And then finally, the last segment is uniform and no longer changing. So what we've all been waiting for is validation. So let's look at our 360-degree model with our M2 mesh. We're looking here at solder mean diameter on a fairly tight ordinate from 52.5 to 62.5 microns versus time. And I'm just sampling at random spots throughout the models as proceeding. And the mean of this plot is 57 microns, which is very close to the experimental value that Dr. Zhang got at Baylor of 59 plus or minus 5 microns. So we were very happy with this. Our models have not completed, but we're looking at the latest results here from 360M2 again. And the left-hand figure is cross-section of the nozzle with contours of VOF, where blue is the fuel itself. And then the converted lumps is what ANSYS calls them, the material that has moved from VOF interface to DPM. You see that in the center stream where we're doing a cross-cut of the nozzle. So this is a three-dimensional phenomenon, but we're only looking down that center stream. And then the right-hand side is the isosurface. And we see a breakup situation very close to the introduction of the steam. See this nice left to right undulation and a quick breakup. So it's a combination of flow focusing and perhaps flow undulating. I don't see any evidence of flow blurring, as is hypothesized by Dr. Zhang, but she was not able to collect data deep in the nozzle, so they were not for sure. But we would learn from this that that's not occurring. The isosurface replicates this by showing a very immediate breakup downstream of their meeting location. So as we continue looking at the latest results from our model, these are cross sections of slurry VOF, where again blue is the liquid phase, and we're looking at planes 6, 7, 8, 9, and 10, and 11. And if you look in the upper right hand corner, I've drawn a reference for plane number 8. So 6 and 7 are the two before it, and then 9, 10, and 11 are of course the three after it. So moving down that trajectory, and you see something very interesting. We knew that the flow was undulating and there was rotation and axis crossing. However, what's interesting from this is that the frequency is a function of distance. So where the streams first meet up around above 6, we see this relatively slow dancing, and then that continues to increase progressively from left to right and top to bottom. Now we review something similar here on those same planes, 6, 7, 8, 9, 10, and 11, but here we're looking at crosscuts and velocity contours. So dark is slow, white is very fast, and we see interesting three-dimensional phenomena. We see the frequencies improving or increasing, going from 6 to 11, and this obvious stream breakup, and in fact, kind of a bimodal distribution of the stream beginning in perhaps 9. So we'll conclude here. We've demonstrated a validated simulation tool. When the primary instability source lies at the center line, a reduced azimuthal domain does not work. And again, I preface that with it doesn't work in our ANSYS that we're using here. The central jet rotates clockwise, counterclockwise, and moves across axes and dancing. The simulated results look more like flow focusing. I couldn't see any evidence of flow blurring. There's no penetration of gas in the contiguous liquid, and there's no effervescence. A future work, we need to continue our mesh independence study. I'm running an M3 now, but also more importantly, I want to coarsen the mesh downstream of where the VOF is completely converted to DPM, so that we can get to less than 200 million cells, which is where we are in M2, or M3, excuse me. Thank you for your attention. Like I said, thank you for your attention. If you want to check out my website, there's the QR code. Thank you.